This video focuses on the concepts of mass spectrometry, which is discussed in Chapter 14, Sections 14.8 through 14.16. Our goals for this chapter are to understand the basics of our mass spectrometry and the instrumentation required to do this experimentation. We're also going to practice with reading and analyzing a mass spectrum, and then we'll also use that mass spectrum in order to help us predict the molecular formula or the molecular mass of a compound. So let's talk about some basics of our mass spectrometry. So essentially this technique is used to measure the molecular weight and determine the chemical formula of an organic compound. A lot of times this is referred to as mass spec or abbreviated MS to discuss our mass spectrometry. And some interesting things about mass spectrometry is that it can be super sensitive, allowing us to determine the molecular weight of compounds down to 4 decimal places. And sometimes if you have compounds that have several maybe you have a mixture with several different compounds in it, you can actually use mass spec tied with other things like gas chromatography. So if you use gas chromatography, you can use that part first to separate it into the different components, and then through mass spec you can actually study individual components that are in there. So you can tie mass spec with other things to get very detailed information about your compounds. So how does it work? Essentially how it works is you have a sample that you put into the machine, and you heat it up to a very high temperature so that it's vaporized. Then after it's vaporized, and it's ionized using a beam of high energy electrons, which is different than our electromagnetic radiation that we talked about for IR. This is a different type. That's why it's not called mass spectroscopy, it's mass spectrometry, because you're using a different technique to actually probe your molecule. The energy of these electrons is usually very, very high, almost 16 times more energy than it required to break a typical sigma bond. So you're just blasting the crap out of your molecules with lots of energy. And then in order to ionize the molecule, that electron beam causes it to eject an electron in the process. The species that is formed because this electron is ejected is an unstable radical cation called a molecular ion. And then this cation is so unstable it actually decomposes into smaller fragments called fragmentation, through a process called fragmentation. How different molecules or different functional groups actually go through the process of fragmentation depends on what you have. So that's what a bulk of the text talks about. And it's not really required for our class, so I'm not going to go through too many details as far as how the fragmentation process happens, but just know that when you eject these electrons, you cause the formation of a radical cation. That cation can then fragment. Those fragmentations are then positively charged, so then they can accelerate towards a negatively charged plate at the end of the instrumentation. As they travel to that plate, they're actually pass through a magnetic field where they can be deflected by different amounts based on their mass to charge ratio. Then those fragments that are detected get plotted onto a chart. That mass to charge ratio is commonly referred to as the M over Z, where M stands for mass, Z stands for the charge, and because they are cations, typically the Z is a +1, so then the mass of our compound can be detected, or mass of that fragment can be detected and plotted. So this is what the instrumentation looks like. So just to give you an idea, on this left side is where you would have your sample. You then put it inside of some very hot thing or very hot filament that just heats the crap out of it. Then you can have the electron beam interact with that sample, and then you have these plates where you can then cause it to move through, and you can have it go through the magnetic field, and then you can collect it here, and then they can be deflected along the way as long as you have that magnetic field on, and they can be sensed and detected, deflected based on their mass. And then your output would actually be this mass spectrum. So what you would probably see is just your sample and then your mass spectrum, and then this is everything that's inside. We actually have one of these in the lab. We have a GC mass spec or GC-MS. So we do the GC portion first, and then we can analyze the mass spec through this. So hopefully At some point you get to check that out in real life. So let's talk a little bit about that radical cation that is formed, since this is what we're detecting, and this is what is causing the fragmentation. So the radical cation is formed by the impact of the electron beam. So you have your sample, whatever it may be here on your left, the electrons are high energy, and then because this beam of electrons causes an electron to be ejected, I'm left with a radical, meaning one electron, and then it's also a cation because I now have a positive charge. So that radical cation has the abbreviation of a capital M with a plus sign and the plus sign abbreviating for the cation, the dot abbreviating for the fact that you have a radical, and then M just stands for the molecule, any generic molecule. This thing is very unstable when it's created, so that's what is actually decomposing into the different cationic fragments. So you have your parent molecule that you're injecting, it loses its electron, you make your unstable radical cation, which then can further decompose into radicals and other cations. So then these fragments that are the cations are what are collected. When you're doing your measurements, your unstable radical cation can actually be used to predict the mass of your overall compound, because if you're just losing one electron, electrons don't really affect the mass. If you remember from Gen Chem, you would have to lose 2,000 electrons in order to affect the mass of one atom. So by ejecting that one electron, the mass of your radical cation is actually always equal to the mass of your molecule. So this is if you measure your radical cation mass on your spectrum, you can then say what is the mass of your compound. So let's look at that spectrum and what it looks like. So this is what a mass spectrum plot looks like, just a bunch of straight up and down lines, nothing as extraordinary as our IR. On the left-hand side, you have your y-axis, which tells you what your amount of each cation is, or your relative abundance or relative intensity, so how many there are relative to each other. And then on the bottom you have the mass to charge ratio. We can also just say it's the mass because we already said that the charge is typically +1. The relative abundance, so why do we do it relatively? So it's all relative to whatever is 100% or what is the most abundant fragment. And then the heights of the other peaks are relative to that component. So in this mass spectrum of my trifluoroiodomethane, where I have those 4 different elements on there, this is actually the most abundant, and then these heights are relative to that component. So you can say, well, this is the most abundant fragment. Whether or not that is my radical cation depends on the compound itself, but you have a most abundant fragment which has the 100%, and everything else is based relative to that. So like I said, that tallest peak is called the base peak at 100% abundance. It may or may not be the radical cation peak. Everything is measured relative to that base peak. And then if you notice, let's say this is my most abundant peak here. Anything that would be to the right of this peak or to the left of this peak is relative to this peak. So the pieces that are to the left, for example, these ones that I'm circling now, these are all less than my base peak. These are fragments, and then anything to the right of that would be some version of the isotope if this were my M+, if this was my radical cation. So let's kind of look at how do I know if this is my radical cation or not. So if it is my radical cation, for example with benzene, the base peak is the radical cation peak. This is because for benzene this is not the peak that easily fragments. So you would have your M+ radical peak or your radical ion peak here. So this would be both my base peak because it's at 100% absorbance, and then it would also be my radical cation, which is my M+ radical. This peak that's off to the right would be an example of I just lost my train of thought, I'm sorry. This is an example of the isotope features here. Remember, carbon-13 and carbon-12. Carbon-12 is the most abundant, but you still have carbon-13. So that gives rise to a more heavier isotope, not necessarily more abundant, but heavier. And then all of these peaks that we're seeing down here are going to be your fragments. So notice that you don't have as much fragmentation. You have your fragments down here. They're just not as heavily in abundance as the other components. How do I know that that base peak is my radical cation peak? Well, here, my radical cation, the mass of my molecule is equal to the mass of my radical cation. If I calculate C6H6 for benzene, that's its chemical formula, we would find that it has 78 grams per mole. So I go down here, and that's at 78. And that would be the highest peak, and then it's also my radical cation peak. This is different if I have something like C5H12. My parent is pentane, or my molecule here is pentane. It fragments very easily, so you'll notice here that your base peak is at this location at 43. But if I calculate the molar mass of pentane, C5H12, it would be up here at 72. So notice that this is my radical ion peak, which is the mass of my actual molecule for pentane, but it's not necessarily my base peak. If I look at the structure for pentane, you can see that it has a very simple structure. The beam can come in and kind of make those different fragments. My most abundant fragment just happens to be the one that has a mass of 43. So this is an example of where your base peak and your radical ion peak are not the same. I know this because of my molar mass of pentane. I should see my radical cation peak at 72 grams per mole. Base peak is the one that's at 100%. So if I further expand on that and I say, okay, well, let's identify the base peak and the M plus radical peak for each spectrum. In order to help me identify which one matches the following hydrocarbons, I have pentane, one pentene, and one pentyne. So taking this from the beginning, the first thing I would recommend doing is get the molar mass of each of these compounds, and then that can help you predict which one of these is your structure for each, and then that will help you figure out what the base peak and the M plus dot peak are. Right away, you could probably analyze the base peaks if you wanted to, but let's go ahead and start with calculating the molar mass of each compound first, then we can relate that back to our structures. So if I have pentane, I have C5H12. We already calculated the molar mass of this one, and it has a molar mass of 72. You can put AMU or grams per mole, it doesn't matter, and it has this appearance. If I did one pentene, I would have the chemical formula C5H10. You can either know that, or you can draw your structure out of one pentene and calculate the C's and H's. Once you do that, you find you have C5H10. Molar mass of carbon is 12, molar mass of hydrogen is 1, so this gives me a mass of 70 AMU. And then I can also do the same thing for one pentyne. And this one gives me the chemical formula of C5H8. Again, either you know that from the from your studies, or you can draw the structure of one pentyne. Again, I'm not drawing them very beautifully, but just because I'm doing my scratch work, I can figure out what the mass of each is. So this is 68 AMU. So then if I go up to these plots, I would look at these different plots here, and that would help me predict what's going on. So notice that, let me see, if I look at this middle one, notice that the plot only goes up to 70. So that means this cannot be for pentane. This middle one is not pentane, so I'll put a cross out for that. This cannot be pentane because it doesn't go past 70. If I look at these components over here, I have to see a peak at 72, even if it's very weak. If I look over here on the right, I don't see anything for 72. However, on this first plot, I do see one for 72. This is the only plot I see something for 72, so then that means this must be for pentane. Then that means if I compare these last two, I see a peak at 70 here, which is good. Here I don't see a peak past 70, so then this means this must be 1-pentene. Let me get this cleaned up. And then this leaves this at 1-pentyne, which is consistent with the data because I see a peak at 78 here. So then it's asking me to identify the base peak and the M+ peak. So then this allows me to find my molecular ion peak. And then that also allows me to find my base peak. So my base peak should always be the tallest peak at 100%. So then I could highlight these as my base peaks. Notice in all of these examples, the base peak is not the molecular ion peak, and there's nothing wrong with that. So the first one matches for pentane, the second one matches for 1-pentyne, the last one matches for 1-pentene. I have my base peaks highlighted in yellow, and then I have my radical ion peaks circled in black with the label down below. What are some other tips and tricks to figure out these plots? So some other things, like I said, is that just like I've been saying, the radical ion peak always equals the mass of the molecule, even if it isn't the base peak. One of the things to keep in mind is that there aren't very heavy isotopes over to the right, extreme isotope differences. So usually your radical ion peak is one of the last peaks in the spectrum, if not the last one, just because you don't have many isotopes that are extremely much heavier than what you're starting with. If you calculate an odd molecular mass, the molecule probably contains an odd number of nitrogen atoms. If you calculate an even molecular mass, the molecule probably contains only carbons, hydrogens, and oxygens, or possibly an even number of nitrogens. And then if you're given a relative abundance of atoms, for example, if you're given a % of carbon and a % of hydrogen, you can then go back and use your Gen Chem knowledge of calculating empirical formulas to kind of help you build that ratio to get to your molecular formula and your molar mass in conjunction with your mass spec. If we talk about some of those isotopes, some things you can look for are the M+1 peaks, or your mass spec peaks that have that isotope +1, so one past that. Typically you use this to figure out the number of carbon atoms in the structure. So if you do have something to the right, you can figure out, well, how many carbons there are. Like I said, carbon-12 is the most abundant isotope of carbon. However, 1% of all carbon atoms are carbon-13, and that's what's giving rise to that isotope to the right. So by comparing the heights of the radical ion peak and the radical +1 peak, we can calculate the number of carbons in the molecule using this relationship. Is that if I know the abundance of that radical ion peak +1 divided by the relative abundance of that radical ion peak by itself, since about 1% of all atoms are C13, you can figure out that relationship. So let me show you an example of how to do this. So let's say you analyze your data and you find that you have a radical ion peak at 72 and it has a relative height of 38.3% compared to the base peak. Whereas if you have the radical ion +1 peak at 73, notice one step away, that's where the +1 is coming from, and that has a relative height of 1.7 compared to the base peak, can you figure out what the molecular formula is? So if I break this down, I would say that I can just simply plug these numbers in to kind of give me those masses. So the M+1 peak is at 1.7% abundance. I divide that by the 38.3% abundance, and then I am dividing those two things. I times that by 100%, and then I can divide all of that by 1.1%, and that will give me the number of carbon atoms. So pause and take a second to punch it in your calculator, and hopefully you find the same number I did, which is 4 carbons. So that means my chemical formula is C4 something something something. I can figure out the rest of that because I also know that the mass of my carbons is 12. So 4 times 12 gives me 48. I know the mass of my molecule should be 72. So if I do 72 minus 48, that means the mass of my remaining components is 24. Now it's unrealistic, so if I say, okay, well, hydrogens have a mass of 1, it's unrealistic to say that I'm going to have 24 H's. There's not enough spots here. So I have to figure out what else can be combined. So I could possibly have 10 H's and 1 N. That adds up to 24. But because I have an even mass, I can't have just 1 N. So this is not possible. If I think about other elements that are commonly in organic molecules, O's are common. This has a molar mass of 16. I could work backwards and say 24 minus 16 is 8. So is that possible? I have 8 H's plus 16, or 1 O to give me the mass of 16, giving me a mass of 24. That is completely possible. This is possible if you have something like a ketone. Maybe you have an aldehyde, but this is totally possible to have this as your structure. So if I counted up the masses of each thing, 12 plus 8 plus 16, 12 times 4 plus 8 plus 16 is going to give me the molar mass of 72. So this is a potential molecular formula for this compound based on the comparison of your molecular ion peak and your molecular ion plus 1 peak. You can also analyze the plus 2 peak if you have one. So this occurs when some elements have more than one dominant isotope. So there have other higher peaks possible. The two most common examples we'll see are for chlorine and bromine. So chlorine has 2 abundant isotopes, chlorine 35 and chlorine 37. Chlorine 35 is at 76% abundance in real life, and then chlorine 37 at 24. So this means that because chlorine 35 is roughly 3 times the size of chlorine 37, you will see a 3-to-1 ratio of their peaks. So the peak at the plus 2 position is roughly the third of the height as your radical cation peak. So you'll see a peak 2 spaces over, and then it'll be roughly a third of the height, or third of the abundance of the original peak. And then for bromine, you have 2 isotopes, again, 2 steps away from each other, bromine 79, bromine 81. And these are roughly the same in abundance, so they'll roughly have the same height of their peaks. So your radical cation peak and the radical plus 2 cation peak will be roughly the same heights because they're in equal abundance. So here's a picture of what's happening. Here I have a substituted benzene ring with chlorine and a substituted benzene ring with bromine. Let's start with the chlorine one first. So my mass of this compound is 112. If you count up, you have C6H5Cl, which adds up to 112. So that means if I look over here, this is the 112 peak. It just so happens to be the base peak and the radical cation peak for this molecule. Then if I look 2 steps away, so if this is 112, 2 steps away, if you were to measure their heights and kind of look at this in thirds, this is roughly 1/3, so then this peak here would be your M plus 2 peak. If I do the same type of analysis for my substituted benzene ring with bromine, again, calculating the mass C6H5Br, you would find that the mass is 157. So if I come over here, this is my 157. So this would be my radical cation peak. And then this would be the plus 2 peak, again, 2 spaces over. doesn't fit, so I'm squishing it in there. Also take a look, the base peak in this case is not the most abundant, or the base peak is not the radical cation peak, or the radical cation peak is not the most abundant in this case. Another feature of information that you can get after using mass spec is to help you determine the structural arrangement. So along with IR, you can predict what functional groups are present, but you can also determine the degree of unsaturation based on the chemical formula from the mass spec data. This helps you determine the structure of the compounds. So do you have double bonds, triple bonds, rings? What do you have? So the degree of unsaturation that you're going to calculate tells you how many hydrogens are missing due to pi bonds and rings. What I mean by hydrogens missing is that each carbon requires 4 bonds. So hydrogens are kind of placeholders that are put in place to ensure that each carbon has 4 things. If that position of the hydrogen is replaced by something else, whether it's an oxygen, a chlorine, double bond, triple bond, whatever it may be, that gives you unsaturation or non-hydrogen things in that place. So the hydrogen deficiency index calculates the degree of unsaturation to help you figure out, well, how many hydrogens are replaced with different things. So that's where you use this formula here. So you take into account the carbon atoms, the nitrogen atoms, the hydrogen atoms, and the halogens. So X stands for any of the halogens, so that means your bromines, chlorines, fluorines, those types of things. Notice I didn't include oxygens, and oxygens are not included in this formula because oxygens usually follow the same bonding arrangement as carbons, so they don't take the place of anything else. So after you calculate this, you should get a whole number, and what that whole number or that HDI is representing is the sum of the number of double bonds, triple bonds, and rings that are taking the place of your typical hydrogen positions. For example, if I calculate an HDI of 0, that means there are no hydrogens missing. That means I have an alkane hydrocarbon. Each position is fully satisfied or saturated. You could possibly have oxygen, so you could have like an OH or something like that, because oxygen takes on the same type of bonding as your carbons typically, so you don't have to account for that. Let's say I calculate an HDI of 1. That means my structure probably contains a double bond or a ring. I'm not completely saturated, so I can have those positions taken away. Let's say I calculate an HDI of 2. This means I could have 2 double bonds, or 2 rings, or 1 double bond and 1 ring, or a triple bond. Essentially what's happening here is that you have an additive effect. So as I start getting more and more HDI, that means I have more and more substitutions for my hydrogens. So I have multiple double bonds, multiple rings. If I have an HDI of 4, which is possible, that means I have some combination of pi bonds, triple bonds, rings, something going on there in order to tell me the number of substitutions. So let's get some practice calculating the HDI. Let's say I have C3H6, and I want to know, is this completely saturated? Do I have some double bonds? If so, how many can I predict in this formula? So my formula is HDI is equal to 1/2 times 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens minus the number of halogens. So if I look at the chemical formula here, I can say that I have 1/2 times the sum of 2 times 3 plus 2. I don't have any nitrogens. I have 6 hydrogens. Let me go back and add those hydrogens in just so you can, or the nitrogens in just so you can be clear. So I have no nitrogens, so I'm adding 0. I'm minusing 6, and then I'm minusing 0 because I have no halogens. If I put this together, I get 8 minus 6 times 1/2. I'm just simplifying. 1/2 times 2 is 1, so then my HDI here is 1. So if I go back to my possibilities, HDI 1, that means I contain either 1 double bond or 1 ring. So when I'm predicting my structure for C3H6, that means I either have 1 double bond or I could possibly have 1 ring. Now we can use our IR to help us predict, do I have a double bond or a ring? As you watch the next videos, you can see that you can also use NMR to help you to predict, do I have a double bond or a ring? Let's try and calculate the hydrogen deficiency index for C3H5Cl O2. So I'm going to use the same formula here. So I have 1/2 times 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens minus the number of halogens. So if I have 1/2 times 2 times 3 plus 2 plus the number of nitrogens, which I don't have any again, minus the number of carbons, which is 5, minus the number of chlorines, which is 1. I don't care about my oxygens, so then this gives me 6 plus 2 minus 6 times 1/2. So then that leaves me with 2 times 1/2 again, which gives me 1. So again, I have to check the NMR or my functional groups to see what the structure is, but I know for sure that it's either going to contain a double bond or a ring. So let's do one more example of analyzing a mass spec. So let's kind of put it all together. So first I want to use my mass spec to identify which of these compounds on the right, and then I want to calculate the HDI. You can either do it visually once you determine the structure, or you can calculate it using the formula. So here, the first thing I would do is I see my base peak down here, and then I have 3 peaks down here as well. So one of these 3 options is going to be my radical cation peak because they're towards the end. Some other things I can look for is I can analyze what compounds this could potentially be. So I have my, they're all benzene, they're all substituted with a different component. I know immediately I can eliminate chlorine because I don't see a peak that is 2 spots away that is 1/3 of the height. I do see one that is 2 spots away, but it's not 1/3 of the height. For the same reasoning, I'm going to eliminate bromine because I don't see 2 peaks towards the end that are roughly the same height. That means I have these 2 structures to determine between. So the next thing I would do is calculate the molar mass of each thing, and that will hopefully help me to determine what I have. So if I calculate the molar mass of this, I have C6. This is not how you might write the chemical formula, but I have H5 and then NH2. The reason I'm doing this is because I know benzene is C6H6, and then I'm taking off one of the H's to replace this in its position, and I'm just adding what's replaced. And then this one I have C6H6, or now I'm saying opposite of what I just said, H5 OH. So if I calculate the molecular mass of each one of these, this one comes out to 93, which reflects that odd, and then this one comes out to 94. Now if I go down here, my 94 is the most abundant peak, and then I barely have a signal at 93. So I would say that this best matches this compound here. Because I have a much stronger signal, I don't have anything going on, so then I would say that this is my benzene substituted with the OH. Then if I want to calculate or determine the HDI, I can do that by using the chemical formula, or I can show you a quick trick by just analyzing the structure. So in this case I have 1 ring, that's my hexane, and then I have 3 double bonds going on. I don't have any triples, so if I add this 1 ring plus 3 double bonds, that gives me 4. 4 is my HDI. If you go back through and calculate, you can do the same thing. How many C's do I have, how many H's, how many whatever in that formula, you would find that you have 4 as well. So that is everything you need for mass spec. You will see how to tie it with NMR, IR, and kind of figure out how to use this to predict everything. If I were to use IR for this, I should see an OH stretching group towards the left-hand side as we learned. So you can put these 2 techniques together.